and receive continuous advice from high-level instructors. In addition, you will have access to the virtual platform where you will find resources and complementary material, so you can be able to relive the classes whenever you want. Don't forget that our certifications are internationally recognized. Get to know us a little more through our networks. With Inel, your education has no borders. Have you ever wondered what benefits you get from being an Inel student? Your learning will not only remain in theory, you will also learn through practical cases, software, projects, and more. You will share experiences and knowledge with students from various countries and receive continuous advice from high-level instructors. In addition, you will have access to the virtual platform where you will find resources and complementary material, so you can be able to relive the classes whenever you want. Don't forget that our certifications are internationally recognized. Get to know us a little more through our networks. With Inel, your education has no borders. Have you ever wondered what benefits you get from being an Inel student? Your learning will not only remain in theory, you will also learn through practical cases, software, projects, and more. You will share experiences and knowledge with students from various countries and receive continuous advice from high-level instructors. In addition, you will have access to the virtual platform where you will find resources and complementary material, so you can be able to relive the classes whenever you want. Don't forget that our certifications are internationally recognized. Get to know us a little more through our networks. With Inel, your education has no borders.
Good morning, dear participants. Welcome to Inel and our new cycle of Masterclass. Who is greeting you is Fabricio Cárdenas, your new tutor. Today we are going to talk about HVDC modeling with PSCAD applications. During the presentation of our instructor, you will have access to the consultations form. There you can make your questions according to the topic presented. Today we have our commercial executive, Lisbeth Ore, who will give us very valuable information at the end of the masterclass, and will announce a big surprise for the participants in this masterclass. You have her contacts here in the slide if you have any doubt. I present you our new instructor, the engineer Trevor Dobbin, who is an specialist in high voltage direct current transmission, HVDC, electronic and computer engineering, with a Master of Science in Electric Engineering in Federal University at Rio de Janeiro, Brazil. Specialist in HVDC transmission controls, simulations, dynamic system modeling, control system, nonlinear systems, stability analysis and control. Currently instructor of Inel Escuela Técnica and Brazilian regular member SCH4 SIGRE. He will be part of our new staff. His experience in HVDC transmission projects was focusing on HVDC transmission, especially in Bipole 1 and 2, HVDC links including their controls and protection replicas, and RTDS simulation and modeling. Okay, Mr. Trevor, now we are ready for your presentation.
Well, just a second. Thank you, Fabricio. Just a second. So can you hear me clearly?
Yes, instructor.
Okay. So we will have a class when we are going to discuss some basic topics and some advanced topics at the same time. Some of you might be find some things already know, and some things could be another point of view of things you might know. But feel free to make your doubts to us, and we will answer. Okay. So we have a slide overview of the HVDC applications and why to use HVDC, then some critical concepts regarding HVDC, and some modeling and applications, and in the end, a starter's example. Okay. So why do you use HVDC transmission systems? Yeah, basically because there is a break-even regarding distance where the costs compensate the costs of these stations. So wherever you have an issue regarding active power compensation and break distances, HVDC might be your best option, especially during especially when you're talking about cables, when the break-even distance is even lower. When you want to connect it asynchronously two areas, they might be with different frequencies, or they might be weakly coupled. And when you want to ensure that you have a controllable power exchange. So how do we make DC from AC? So we were always trying to control the electrical switches in order to get the maximum crash from each phase. So as you can see in this deductive example, you have some assumptions. You need to ensure that the DC current has low variations, and you must try to have small reactances in the AC side. As you can see, we will sequentially commutate between the switches. In this case, you are using thyristors, but these specific applications of rectifiers could be done with diodes, but in HVDC we use LCC converters, we use thyristors. So you change the current between the valves, as you can see in these examples. So now you're switching currents between valve 1 and 6, and thereafter we're going to change it from lower 6 to 2. So enhance 4. So that's the basic working of the LCC 6-pulse converter. Why thyristors? Well, as I said before, you could use a rectifier. However, in a rectifier, it would be almost the same as using thyristors with 0 delay angle. That's it. When you are forward polarized, you can fire the switches. With thyristors, you can delay this by a small angle. We say angle, but we're talking about periods, okay? When you're talking about power system with definite frequency, we can use the concept of angles. So we can modulate this DC voltage in green by changing the delay angle. That's a key concept in HVDC Classic. Okay. So there you go. As you can see, the higher the angle, then we start to lower the DC effective DC mean DC voltage. So how does the AC network interferes in this? So when you are trying to convert from AC to DC, actually we are controlling small controller short circuits. So that's a key concept in HVDC Classic. So you have some, actually, the last preview test slides were a idealization. You have some inductances in the AC side, and then you have some commutation time. We call it commutation overlap. So you have, for a small period of time, the sharing of current between phases. That will be similar or equivalent to a short circuit between phases. So you have this angle alpha, that's the delay angle. You have mi, that's the commutation overlap, and the higher you can use some formulas already in established literature to reach this small result. But the key concept is that in purple, we'll see that's almost like the short circuit is very related to the short circuit between phases of this network. This commutation time and overlap will have an effect in the mean DC voltage. So you have a small little drop because of this area that we highlighted in this figure. So you have to live with that, okay? So those angles were the key angles in HVDC LCC, based on LCC, are the alpha angle when you delay the transmission, delay the firing. You have mi, the commutation overlap angle, and you have some complementary angles that might be useful. They are made based on those zones for the rectifier. So for people that are not used to HVDC, can the VDC be 0 or negative? Yes, it can. When you start to increase the alpha angle, you can reach a state where the mean DC voltage will be 0 or even negative. However, they are not quite the same as rectifiers. You need to have some conditions to be ensured, so you have a proper operation, because current still can be inverted in this technology. So the inversion angles are the same, but I can see the width is changed. So a new key concept is used, the extinction angle, because you want to make sure that you have some time before you commutate between phases. So you have higher alpha angles, and you must be sure you have to take care of it with gamma and mi. So when you join those together, you have the concept of HVDC transmission, when you have a rectifier bridge and an inverter bridge. Those are very simplified equations just to represent simply this circuit as a DC circuit. This voltage drop, dependent on the commutation, can be modeled as something that's proportional to the DC current. So we call it a resistance, but it is not actually a resistance. And when you use the inverter mode, something very interesting occurs. The resistance leads to its model, it's increasing in voltage. So we must be careful with that. So that's all? Not at all. So when you put those blocks together, you start to be more similar to a actual HVDC project when you have to use not only YY connections, but also Y delta connections. I invited the audience to wonder why you must use it and what would be those effects. So you can have the option to have ground electrodes or metallic return. You must ensure that the DC current must follow the Kirchhoff laws. So just one quick statement: you are not transmitting current between two stations because you are very far away, but you are drawing electron from the grounding areas. With metallic return, you are actually transmitting current. So we have this symbology for rectifier and for inverters. You also need AC filters, and some projects, most of them need also DC filters. You must have the DC reactor to ensure that the current is very smooth. It's called a smoothing reactor. So when you put those two together, you have a topology called the bipole. It's a very typical topology in many projects. So it's the most used one for very high power because it's very economical. So now we start about some modeling and simulations. One of the most used tools is PSCAD. You can have the free edition to start to get used to that in the manufacturer website. It's not indicated for professional students because of many reasons, and it is useful because you have a documentation and simulation. It has a huge library for HVDC controls, and you can process the waveforms and use now Python scripting to make anything you wish with the results. So basically you have two kinds of components and meshes. You have electrical meshes, those ones that you are talking about kilovolts and kiloamperes, and you have control nodes that you're talking about logics and integrators, proportional controllers, and filters. This is the face of the last version. You can generally, if you are starting to use it, you are loading a file. It has a lot of examples. You should use them. Benchmarks from SIGRE, from the EEE, and you load the case, and you can already trigger the run button and see the results displayed in waveforms. So you are talking for starts of a very used benchmark. It's called SIGRE benchmark. It represents a single monopole. It's very useful to get conclusions quickly. So you will learn a lot by using this example. You have already AC filters, 12 boost converters. You have firing controls, some very simplified ones, and some already intermediate complexity. But there is no system, so master controls. For example, power control. So the key point is this 6-pulse bridge. It is already implementing a lot of stuff from HVDC controls. You probably want to use it. So you have already PLLs, ring counters, alpha and gamma measurements, and you can block or deblock faults. So that's a visual representation on what is represented or what isn't. You have a very simplified already control. in green, in gray, it's not represented in Secure Benchmark, but you might want to implement it. It's up to you. In the inverter side, the same. This benchmark uses the extinction angle for controls, but you might use DC voltage and AC voltage. But it already has the mesh selector. One key point to make sure that you know, there is a critical component in HVDC called the voltage dependent current limiter. It is represented in PSCAD, but it's very simplified, but you might want to know more about it. So that's the picture of the VDCL. There is already a PI controller and a gamma controller, and there is another intermediate structure called the criteria control. There are many names, but this is one most used. And there is a rectifier PI control. It's very simplified. So let's talk about results. So this is a small example of what would be the dynamic performance study. We're using the LCC from Secure Benchmark. This is just if you just run, this will happen. You must see this picture, otherwise something's wrong. So it's a very good starting point. So you have a phase that you are deblocking valves, then you have a recover because you're not recovering from anything, and then you have the steady state. But in Secure Benchmark, you have a component called fault. You must click in the inverter side, in the inverter block, and you see the timed fault. So this is an example of the single AC fault. You have a very low impedance during 50 milliseconds. So as you can see, you have key points. You have the start of the fault when the DC current will go very high, and you have the low voltage limiter that I talked before. He will hold the current, so can you avoid to feed the AC current. Thereafter, the fault extinguish, or if it's not a permanent fault, the controls will try to restate the HVDC link to its normal conditions. So you have this recovery step. That's part of what I'm trying to study. How is this recovery? Is the system in danger? Because generally when I talk about HVDC, you're talking about massive active power, something like 1 gigahertz and beyond. So now if you change the impedance, you make it a little higher. Can you see some changes? As you can see, there are dynamic changes. You are going to study that. So if you have a face-to-face, things change a little. But if you go further and to make it, in this case, a two-phase ground, you see that something very interesting happens. You have something called a commutation failure. We are trying to restate the transmission, and then you have another fault. This is very dangerous. So you must to know if you are prone to that. There are many ways to solve it, and you can discuss this in your course. Well, I already told you what happened. So these are key topics regarding the LCC technology. So we are talking about the short circuit level dependency. We are talking about its prone to commutation failures. It generally transmits higher. You have higher ratings for voltage, current, and power. Another topic we didn't discuss it, but it might be interesting because the LCC technology can inherently avoid to feed the DC current. And more details you see in the course, even including MCC technology, SCMC technology. So those are our references. Thank you. And that's it.
Okay, thank you.
Oh, I'm sorry. My camera. I'm not. I tried to open my camera, but it said that the host has stopped it. I deeply apologize.
Oh, don't worry about that, Mr. Trevor. We really appreciate your participation. Thank you very much. Now, remember to the participants that your questions will be attended in a personalized way through your email addresses that has been registered. Now I leave you with our commercial executive, Lisbeth Ore, who has a very valuable information to share with us.
Mauricio, thank you very much. I take this moment to send a special greeting to all of you who are joining us today. Well, this masterclass is just a preview of what we are going to delve into in our HVDC specialization program, which starts on October 26th with a duration of 44 hours. Also, remember that we will give a 10% discount to all of participants who register early. So, what benefits will you have? At Inel, our teaching methodology is focused on practice. Likewise, you will have access to our free courses and master classes on the platform, and attention to queries up to 1 month after finishing the program. At the end of the course, we'll give you a double international certification, one of them in the name of the Inel and another in the name of IEEE. Good. For more information about this course, you can scan the QR code and we will assist you as soon as possible. Okay, we will also have a second masterclass prior to the HVDC course. So we invite you to join our next specialization journey. Now, Felicia, could you tell us how the participants will be able to access the certification of this masterclass?
Sure. Thank you, Elizabeth, for this information. Okay, Inel will give you a certificate for your active participation. To get it, you should follow the next steps. Enter the link that I will put in a minute, or scan this QR that is showing the screen. Remember that this certificate will be sending by your email address. Congratulations for your participation, and the family Inel wish you a good morning.
How are you, dear participants? It has been a pleasure to have had the assistance of each one of you in our event. To obtain the certificate, start by clicking on the following link. This will take us directly to a form. Click on it. How are you, dear participants? It has been a pleasure to have had the assistance of each one of you in our event. To obtain the certificate, start by clicking on the following link. This will take us directly to a form. Click on it. Remember that it is very important to fill in your information correctly, as it will be used to issue your certificate. Before submitting your survey, leave us your opinion on our Facebook page and tell us what you thought of our event. Copy the link and that's it. In the next few days, you will receive your certificate by email on the scheduled dates. We remind you that the ratings or positive or negative opinions of the event will not influence in obtaining your certificate.
Okay, that will be all. Thank you very much for your participation. As I say, just you have to enter to this link or scan the QR that I show. Thank you very much. That will be all. Thank you, Mr. Trevor. That was an incredible presentation. We wish to see you again. Thank you.
Thank you, Fabricio. Thank you for participation.
Thank you.